Well, as I promised, here we have a word problem involving derivatives of exponential functions. Actually, that should say exponential functions. And as you can read, but I will read, the sales of a new personal computer in thousands are given by S of t, S of course for sales, is equal to 100 minus 90 times e to the power negative 0.3 t, where t represents time in years. Find the rate of change of sales, A, after 1 year, and B, after 20 years. Well, actually, let's first start this with a problem, with the issue of how do we calculate, what does S represent? And for instance, S will tell us, S of t will tell us the number of sales of personal computers at year number t. So for instance, after 1 year, S of 1 represents in thousands, the number of PCs of this particular PC sold, the number of this particular computer. Sold. And so the way we would calculate that, as pointed out, is we'd put a 1 into the function, and we would, for t that is, and do the appropriate calculation. Now, of course, t is 1 here, so we would have 100 minus 90 times e to the power, and of course 1 times negative 0.3 is just negative 0.3. That would require a calculator to do this, and so what I'll do here is pause so that we can see how a calculator might be used. Now, this isn't really doing the problem that we're asked to do, but it'll kind of give us an idea of what's happening. Okay, now we could ask a similar question. That is, how many computers sold after 1 year? And to answer that question, of course, our time, t, represented in years, would be 5. So we would look at S of 5, which of course would be 100 minus 90 times e to the power negative 0.3 times our t value of 5 years. We go through the calculation here. Of course, I'm going to do the one calculation in my head because 0.3 times 5 is 1.5. So I could just make this a little bit simpler calculation from a calculator. This will be e to the power negative 0.15. I'll just make it a little simpler in a moment. And then we'd get our calculator out and find that the value was. In fact, I haven't even done this calculation yet. Let's see if I can't do that. Well, as you can see with our calculator calculations and the error that I made when I wrote this down, of course, 0.3 times 5 is 1.5, and so I had the exponent incorrect. But anyway, the calculator comes up with 79.918, which, remember, that's in thousands of computers, so it's 79,918 computers sold after 5 years. Of course, this isn't what was being asked. The question ends up being is find the rate of change of sales after 1 year. And it's what's really important to understand is rate of change is really key to what we're doing here. Rate of change. And that's exactly what the derivative is. The derivative, regardless of the setting, the derivative represents instantaneous, but more generally, instantaneous rate of change. We recall from a long time ago when we were talking about limits. Derivative represents instantaneous rate of change. And so unless we see average rate of change, we know that whenever we see rate of change, we're looking for the derivative. We use the derivative. So that's the key to what we're going to be doing in problems, word problems, where we see things of this nature. Well, let's, on the next page, let's actually calculate the derivative for this sales function, and that's what this is a sales function. Let's pause and go to the next page. Now remember, our sales function is S of t equal 100 minus 90 times e to a power that is negative 0.3t, where S is the number of sales after t years. So that's what this represents. And again, we're looking for rate of change. Okay, and as I mentioned earlier, rate of change tells us we need to know about the derivative. And so in this case, the derivative is s prime of t. And so our job is to calculate s prime of t. So s prime of t, well, what do we have here? We would be taking the derivative of, with respect to t, not with respect to x, of 100 minus 90 times e to the power negative 0.3t. Okay. Of course, the derivative of 100, because 100 is just a constant, is 0. Then we have minus the derivative of, with respect to t, 90 times e to the power negative 0.3t. I'm putting a few extra steps in here. Of course, that 0 we don't need to be concerned about, but we're going to have a negative, aren't we? And because we have 90 times e to a power, that 90 is a constant times a function. And so we can really bring the 90 out. But what it boils down to is we really just need to find the derivative of e to the power negative 0.3t. Well, anytime we're finding the derivative of e to a power, we know that we have simply e to that same power. So we have e to the same power, but what we have to be careful of is not to forget to take the derivative of the power. Now we're taking the derivative with respect to t, and of course our variable is t. So if we're taking the derivative of a constant times t, then the value would just be the constant. This is like taking the derivative of 2x with respect to x, we would just get 2. So the result of that derivative of negative 0.3t is just negative 0.3. So we have negative 90 times e to the power negative 0.3t, and the result of this derivative is negative 0.3. Oops. Now we notice that we have a negative and a negative, that is a negative 90 and the negative 0.3t, and when we multiply those two together, we should get a positive result of 27 e to the power negative 0.3t. So s prime of t represents, okay, it is 27 times e to the negative 0.3t, and this tells us the rate of change, because it's a derivative. A derivative is a slope of a tangent line, but that's what a slope is. It's the rate of change of the sales to the time in years. Sales in thousand, time in years. So it's the rate of change of sales to time. Okay? So our question A was, what is the rate of change after 1 year? What is the rate of change after 1 year? And simply to calculate that, then, we need to put a 1 into the derivative. And so that would be 27 times e to the power negative 0.3 times 1. We saw in the calculator a little earlier how we go through this calculation. And when we do go through this calculation, I would use the calculator. There's no way around that. And after I use the calculator, I get a value of, what do I get here? Let me click it in. And in fact, I think I'll put it on the screen. But here's what I get as a value in the calculator. Approximately, because what does it really say? Find the rate of change. I guess we're going to round it off a bit here. So I'm going to say 20. Okay, our next question, or part B, is what is the rate of change of sales after 5 years? And by the way, I miswrote, as you can see above. I should have said the rate of change of sales, but that's what this derivative is. It's the rate of change of sales, derivative of sales. After 5 years, then of course we simply use the derivative once again, but rather than putting a 1 in for 1 year, we put a 5 in for 5 years. And so we end up with 27 times e to the power negative 0.3, and we replace t with a 5. Okay, so in this case we get 27 times e to the power negative 1.5. And of course, I would get my calculator out to complete this. And when I get my calculator out, I get approximately 6. Okay, so it's in part A, the sales are changing at, understand what this is saying is after 1 year, sales are changing at a rate of 20,000. Remember, because S is in thousands of computers. 20,000 computers per year, which means the sales are increasing. You know, after 1 year, they're increasing at a rate of 20,000. The sales are increasing at a rate of 20,000 computers per year. Now, after 6 years, though, see, after 6 years, after 5 years, pardon me, after 5 years, sales are changing at a rate of 5,000 computers per year. And so understand what this is saying. It's not saying that we're selling 20,000 computers a year. It's not saying we're selling 5,000 computers a year. That it's saying that after 1 year, the rate at which the sales is changing is by 20,000 a year. So if it continued to do this, then after 2 years, it would be increasing another 20,000 a year. Well, we see that actually after 5 years, our rate of change is 5,000 computers. Excuse me, I rewrote again. That should be 6 for 6,000, right? 6. 6,000 for 6. So after 5 years, we're still having sales increase. See, sales are still increasing, but they're only increasing at 6,000 per year. Not selling 6,000 per year, but the number of sales is increasing by 6,000 a year. So that's something really important for us to understand here. Okay, let's continue this problem on the next page, because I have a couple of other questions I want to go through here, and it's related to the discussion we just had. Okay, part C of this question is what is happening to the rate of change of sales as time goes on. Now, remember, after 1 year, See, 1 year, the rate of change was what? It was, wasn't it 20? Yeah. The rate of change of sales was 20 or 20,000 computers per year. That was how quickly sales were increasing. Okay. And after 5 years, we saw that the rate of change was 6,000 computers per year. So at least between 1 year and 5 years, we had a decrease in the rate of change. Well, I suppose from that we might conclude, to answer this question, what is happening, we might conclude that the rate of change of sales is decreasing. And that would be correct. But let me give a little more information. Here I put the derivative, which is indicating how we calculate the rate of change as t changes. And what I'd like to do with this derivative, okay, is rewrite it a little bit, because the negative exponent on the e makes it harder for us to interpret and evaluate. So I'm going to write this as as 1 over e to the positive 0.3t power. And I really kind of messed that up, because we're not saying 27 times the denominator, we're saying 27 times the fraction, aren't we? So s prime of t is actually equal to 27 over e to a power that's 0.3t. Now, here's the thing to notice, so that we can answer this question really with good information rather than just a couple of examples. See, as t gets larger, and so what are we talking about t getting larger? Time increasing. See, t represents time. So as t gets bigger, we're talking about further into the future. As t gets larger, then what happens? E to the power 0.3t gets larger. I mean, if that means the exponent is getting larger. If the exponent is getting larger, then e to that exponent is getting larger. Well, now, that happens to be a denominator. So that means 27 over e to the 0.3t. The denominator gets big. What happens when a denominator gets big? You know, like if we had 2 over 3, 2 over 5, 2 over 10, 2 over 100, 2 over 1,000, the bigger the denominator gets, the smaller the number gets, right? The smaller the fraction gets. So when the denominator gets big, the fraction gets smaller. So the larger t is, then the smaller the fraction is, and that means the smaller s prime of t is. S prime of t, which is equal to 27 over e to the 0.3t, gets smaller as t gets bigger. Which means we can answer a question above easily now, or with confidence, which means the rate of change in sales, that's s prime of t. See, that's the rate of change in sales, gets smaller, or will decrease as time goes on. It does decrease as time goes on. In fact, I'd like to pause here and look at a graph of s of t. I think that would be Actually, before we do that, let's answer one more question, and then I'll look at a graph so that we put all this together maybe. Does the rate of change of sales, does the rate of change of sales ever equal 0? What do you think? The rate of change of sales gets smaller as time goes on. Does it ever equal 0? Let's go back to this derivative in its new form. You know, originally it was 27 times e to the power negative 0.3t. And then above we wrote that as 27 over e to the positive power 0.3t. Okay, so this represents rate of change for a particular year, rate of change of sales. Well, will this rate of change ever be 0? That is there a t that will make s prime of t 0, or that fraction 0? And the answer is no. I mean, the only way we can have a fraction that is 0 is for the numerator to be 0, the top to be 0. I mean, this is always 27 divided by a number, isn't it? And 27 divided by a number is never going to be 0. Okay, so the answer is no. But as time gets larger, okay, so then the fraction 27 over e to the negative 0.3t gets smaller. So here's my point. For large values of t, then this denominator gets very, very big. And the bigger the denominator is, the smaller the fraction. So we never do get to 0, but it gets closer and closer to 0 because the denominator gets bigger and bigger. So the answer is no, but it gets closer and closer to 0 as t increases and gets larger and larger. Okay. So I think on the next page what I'm going to do is look at or maybe on this page, look at a graph and try to put these pieces together, and then we'll be done with this.